So let's talk real quickly about what this course is going to look like. So I'm hoping many of you coming into this course have done some sort of circuits before, whether it is taking Circuit Lab Virtual last summer or doing Circuit Lab in Scilely or having any sort of knowledge about circuits coming into here. However, if you don't, it is not the end of the world, but you really should pay attention to this part and really don't be hesitant to reach out with the questions because we're going to assume some knowledge going into this and we don't want you to be left behind because of that. So, first, the syllabus as to sort of what we're going to cover and do this year. So, this is our info. So, circuits is very broad. It is much broader than the scope of the Siley rulebook seems to indicate. And we'd like you to be equipped to actually work with circuits, whether it is going and doing your robotics club or going and building something for fun on your own or just enjoying the problem solving. We want to give you the tools to do that. And so, as far as that goes, simulations are going to be real important for what we do here. So, I'm going to show you my favorite tool, LT Spice. If you have anything but a Chromebook, you'll be able to download it. We'll get to that later. But getting familiar with how to use that tool, it's really simple, is going to be great for you. Not only because you can check your answers as you do these circuit practice problems, but because you can just not do the circuit problems at all. You can just focus on simulating and getting to a number because that's what you do in the real world. You wouldn't sit in paper and do algebra. So this year, after this first lesson, which is going to be more content focused, it's going to be focused around four design problems. So we'll send out the syllabus and you can read through this stupid story I wrote. But there's basically four things that we want you to design. So the first thing is going to be an audio equalizer. Someone asked LT Spice isn't allowed during the event. That's true, but I'm sure that if you learn how to use the tool and understand what's going on, you will greatly benefit for the event. Ultimately, when it comes to the event, that is just algebra and fun facts and trivia, and that does not make the best style virtual class. But if you do these things, you will benefit for the event as well. They're not completely uncorrelated. Anyways, we're gonna talk about four design problems here. So an equalizer. Has anyone heard of an audio equalizer? This is a thing people know of as a general term. Does anyone want to guess what an audio equalizer is if they know already? Just
Oh,
give a guess.
uh,
Yeah.
like just to keep the same volume,
Same volume across what?
like the entire,
I think you're there. Just give it a guess. Anything you got.
like over the entire duration, like the sound is being played.
Yeah, so it can help with that. That's not the primary definition though. And anyone can just unmute and talk. No need to be scared. I don't know who's raising their hand.
Uh, it's specifically lowers the volume of certain frequencies and it boosts certain frequencies to make all of them a
There you go.
similar volume.
That's the
At
one.
least that was
So if I
oh
give you like three knobs, one is a low, one is a medium, one is a high. Bass, mid, and treble is what you'd call it. The audio equalizer is to turn up the bass and turn down the treble. So maybe you're driving your Mercedes down the suburban block through California and you really want to annoy your neighbors. You'd go to your bass knob in your equalizer, turn it all the way up and annoy all your neighbors. It allows you to
Does
control
it have
the
a,
volume at different frequency ranges. Omar, is there a question?
does it use op amps as well, or
It
not
can.
comp?
So
Oh,
that's what we're going to talk about. The two key things in an equalizer are filters and amplifiers. You need something to isolate the frequency range, something to turn up or turn down that specific frequency range once it's isolated, and then something to recombine all the sound. But op amps do get involved there, so that's going to be one of the things we talk about. And so for that next lecture, Wednesday lesson, not lecture, we're going to focus on sort of the theory behind that. It's going to be accessible theory stuff that you guys might not have seen before, but stuff that you have the tools already to look at with just basic circuit analysis. We'll present it in a understandable way. And then on Friday, your task will be to give us a design for an equalizer. So when it comes to these designs, I want you to use AI. I want you to use every tool you can find out there. You know, you have AI in the real world. We're not gonna act like it doesn't exist. And I want you guys to come up with a really cool design. But if you present your design and you say something like, and I did this because Claude said it was a good idea, that would not be a suitable explanation for why something works. So use Claude, use ChatGPT, but use it to help you understand what's going on as well as you make your designs. And these will be part of the course challenges that uh, that Nathan's going to talk about for I don't really know how the points work there, but he'll explain it. So then 4 and 5, those will be about transmission lines. So when I want to send a signal over a really long wire, there are certain considerations that need to be made. Then 6 and 7 is going to be about basically a stable amplifier. So how do I make a device that is not super sensitive to errors and how the components of that device were made? And then the last one is going to be basically signals. And how do you record a signal and store that signal and play back that signal? These might change, to be honest. We'll start with the equalizer and see how things go. But these are all going to be a fun thing, I think, to explore specific things within circuit analysis without sitting there and doing a bunch of algebra every day. I really don't want you to do a bunch of algebra. I want you to design things. That's what engineering is about. That's what circuits are about. So with that, if at any point you find yourself feeling like you don't have prerequisite knowledge, I think you should go through last year's circuit lab slides. So that's what this folder linked here is. I also have the lessons on my YouTube. I'll send those out.
Are the slides already on the Google Classroom? Or like
The
only in
Google
post?
Classroom, I'll re-show the code at the end, but I'll post these there. Yeah.
Okay.
So these slides, they go through the details of all the basics, very in depth. We have some practice problems in the P sets and stuff. And of course, the videos are posted. And so if you don't have the requisite knowledge that we're hoping for, then go through these and please reach out with any questions. We're really happy to help. And we are, just happy to help. So that's that. So that's the general structure of things. I'll let Nathan talk for a bit.
So as like if you've taken another style virtual course before, I think this is how all of them work, but basically like so in this class you can score points. So the points are based on there's a midpoint challenge, there's a final challenge. So you'll earn points during those challenges. And then it's also based on your attendance. So the higher your attendance, the more points you're going to earn. And also, if we see that you're an active participant with your like video always on, you're always paying attention, then we can also give you more points like that. So that's pretty much how it works. And there's also a ScioCamp tournament. So basically on Tuesdays and Thursdays, you can join and you can win prizes, and they're like I think there's like prizes, there's like some scholarships maybe, and then like and if you want to win any prize at all, you have to attend these challenges. Okay, so this year we have 2 in-course challenges. So one is the midpoint and one is the final. So the midpoint is going to be worth 300 points. The final is worth 340. Attendance. So we have 9 classes. Every day you attend, you're going to get 30 points for a total of 270 points. And then you also get bonus points. I believe these are just based on like participation and stuff like that. Yeah, do you have a question?
Yeah. For some reason, I can't view your screen. So should I just like leave and rejoin the meeting?
You can't see
Anybody
the
else?
can others also not see the screen share?
I
Or
can't view like the screen for some reason.
is anyone else having this problem?
No, I'm
I
not.
can see you.
Yeah, then maybe you should leave and rejoin. We'll admit you back. Sorry about that.
Okay.
See your screen.
Okay.
By the way, just in general, if there's ever a question, just you can just unmute and ask. You don't need to raise your hand or anything. This is going to be a discussion-oriented class, so just talk to us, we'll talk to you, and it'll be a good learning experience that way. All right, Nathan, go ahead.
My brother can't join. He's
Um,
having some technical difficulties.
The link don't work.
Chill.
yeah, I'm not sure I have control over that. Nathan, do you want to keep explaining what's going on?
Okay. Yeah, wait, I think that's about it for this slide. So like these are just ways to earn points. So midpoint, final, attendance, and bonus. So like for participation, stuff like that.
I can view it now. Thank you.
Okay. Okay, that's good. Okay, attendance. So you'll have to fill out this like attendance form after every course. We'll send out the link at the end of the class. And if you are very good with participation and you're always paying attention and we see that, then we can give you bonus points for being a good student.
Yeah, I think he already said this, so I'm just gonna move on. These slides are redundant, so
Yeah. Okay, yeah, these are just challenges again. Try to like attend if you can. Yeah. That's what I think.
okay. I'm stealing the mic back from Nathan. Thanks,
I
Nathan.
have a question.
Sure,
So,
what's up?
like, if we have, for example, like a live event on like Tuesdays and Thursdays, do we also have like the in-course like events on the same day in the mornings? Like there's like a middle course event, and then are those on the
To
Tuesdays
my
and
knowledge,
Thursdays?
all of the course-related challenges are just during the course. At least that's how we're gonna do it here.
Oh,
So like the
okay.
mid-course challenge and the final course challenge we're just gonna do during the course time. You can work on it outside, but the actual like event, I guess, is gonna
Oh,
be
okay.
during
Yeah.
the course time.
Thank you.
Yeah, Ranj.
I'm confused on how we find like the Google Classroom like
We'll
code.
send it out. We'll send it out at the end. I'll send an email
Like,
to
did
everyone.
you guys like email us?
I haven't emailed yet, but I will email.
Oh, okay. Thank you.
Anything else? Good. Okay. So we're gonna do a big crash course on how to analyze circuits. You guys have probably done mesh and these other techniques, and I'm not gonna talk about mesh because mesh is not good. I'm gonna basically, I'm just gonna give to you what I think are the most essential things to think about while analyzing circuits after having taught some circuit stuff at the college level and seeing what students struggle with there. And so these are, if you have a good grasp on the concepts that we're going to discuss over the next 20, 30 minutes, then I think you're well set up for all the stuff we're going to do in Scile Virtual this year, but also for Circuit Lab analysis and Scile in general. So these are really the really important things to wrap your head around. And it's going to be a discussion. So we'll start out with just this point. Just people just talk to me and say, what are the things that relate voltage, current, resistance, and power, whether it's equations or conceptual or anything you got. Yeah, Ishan.
So like first of all there's like Ohm's law, which is like V equals IR. But then there's also like power, which is V times I equals P. But then if we combine those two, then we get like the other relationships, like V squared over R is power, and then I squared times R is resistance. I mean, sorry,
Yes, so
I
that's
squared
point number
times R.
one. All these important relationships, that's great for getting you power, current, voltage. They all kind of relate to each other. And these are really the fundamental units that we deal with in circuit analysis. So in mechanics, you might think about acceleration, velocity, and these things. When we talk about electricity and circuits, these are our central units and central quantities.
I have a question. All this will be posted on like the Google Classroom, right? Like
Indeed.
the recording and slides.
Yeah, it will be. Yeah.
Okay.
What else we got? What about more conceptually? Are there any handy dandy things that you guys think about current, voltage, resistance, and power beyond just Ohm's law?
I just started Science Olympiad, and I don't know what anything you're talking about.
Yeah, so that's okay. So I would refer you again to the things I'll send out in the slides from last year's Circuit Lab slides. This is the Circuit Lab Advanced section. So although in class time we aren't necessarily gonna go super fundamental like that, you should definitely reach out if you have any questions and use those resources to learn. What else we got? Joel, I guess.
Well, for voltage, you could usually think about it as being relative to an area, usually ground. So for like circuit analysis, you first have to establish a ground or a point that is neutral or 0 volts.
Yeah, exactly. And so maybe do we know why that is? Why can't we just say the voltage, like I can say the voltage here is 4 volts, but why do I have to have a ground? Is there a particular like
Passing.
physics reason
Because
we
it's
can think of?
voltage measures potential difference, so it
Yes.
measures the difference between two places, not just a
Exactly.
single value.
Voltage is a potential difference. And so the analogy that's helpful to think about, I think, is just a ball on a hill, right? The ground is literally what we call ground, 0 volts is the ground. If I have a ball on the hill right here, that might be a low voltage. If I raise it up, it's a high voltage. In the same way that you have gravitational potential and the ability of a ball to fall down, it's the same thing with electricity. It's electric potential. What else we got? Anyone can just unmute and talk out of this.
I have something.
Go ahead.
Okay, so you could think about like an analogy to a water pipe. So the pump that pushes the water, that's the voltage. The water traveling through is the current, and if there's like any parts of the pipe that get narrower, that creates resistance.
Yeah, so that's a really good analogy. And we'll find that this water analogy applies in a lot of different contexts. For those of you that were here for Circuit Lab last year when we talked about MOSFETs, the water analogy became very useful there when thinking about how the gate closes and the drain sends stuff and the source does stuff. So yeah, the water analogy is a great thing to think about.
Wait, and also like for the voltage, it's like we have to remember that it's relative. So like based on what the ground is, so we always have to define a ground. While like for current, it's like an arbitrary value. It's like universal. Like no matter where it is, we can always say there's like 5 amps and it'll be 5 amps. But 5 volts could mean different things depending on what the ground is.
So I think you're close. You're right. We should always define the reference for voltage, and you're right that current is indeed an absolute thing. But if I say 5 volts, like if I'm just in conversation telling my friend I'm building something with, hey, voltage here is 5 volts, then that is relative to a ground that this voltage is being measured. It would be, I guess, if I say the potential difference between A and B is 3 volts, that you need to think, well, if A is at 2 volts, then that means B is at -1 volt. So you have to be careful with the terminology, I guess.
Oh,
So
wait,
now-
yeah,
Also,
let's-
there.
Oh.
Oh, yeah, you can go.
So here's a question. Does current flow from high voltage to low voltage or from low voltage to high voltage, and why?
It flows from high to low with conventional current, but then electrons in reality flow from low to high.
Yeah. So you say conventional current. What does that mean? I don't know anything. What does conventional current mean?
I think it's like what scientists like first thought it was, so then they just used it by convention, like, but in reality, it's the electrons that are flowing, so it switches.
That's what like Benjamin Franklin first thought like, when he drafted the theory.
Yeah.
Yeah, I
But
think
the
That's like
thing
what
is-
all the
there's-
diagrams use. That's
there's
like what
some
all
apocryphal history.
Yeah, all the diagrams use conventional, but in like really it's different.
In reality, electrons
Yeah.
flow the other way, and scientists
Yeah.
found that out later. And they use
So they
conventional
just-
current because it's easier to use.
and
Yeah.
they just never wanted to change the system.
Yeah.
So this is something that's going to come up time and time again. What happens if I change the direction of a current arrow in my analysis? And the answer to that question is as long as you're consistent about everything, as
Yeah.
long as you swap the sign of literally everything, physics doesn't care what you call positive or what you call negative. And so that's going to be a big thing we'll see as well. That continues coming up. Just be consistent about your signs.
And
So,
also like
Maybe someone can tell me. I have a little video here. So at the this red line up top, I have high voltage. The blue line at the bottom, I have low voltage. Okay, and I have a bunch of negative charges and positive charges in the area in between. When motion starts, are the positive charges going to go up or are they going to go down?
They're gonna go up. More down
Go up, yeah.
because it is
up.
No, they're gonna go
No,
down.
let's
They're
talk
gonna go
about-
up.
Let's talk about the
Down.
positive charges.
downward because it would be more negative. And
Yeah,
since
positive to negative, then negative.
Wait,
to positive.
are
Also
the
plus the
blue
high
are the
voltage.
blue charges positive?
No,
So the blue
red
charges are
charges will be
negative,
positive.
the red charges
I
are
don't know.
positive.
Up or down, I don't know.
The
They'll go
positive's
down.
gonna go
Positive to negative and negative to positive. They'll go down.
down.
Yeah,
They're
actually,
gonna
yeah,
go
they'll go
down.
down.
I'm
They'll go
real
down.
I'm
Yeah, it's
realizing
gonna go down because they are trapped.
It's gonna go down.
It's
I'm
gonna go
realizing
down.
my
They're gonna go
policy
down.
of
Yeah, because
Down.
positives are, yeah. Wait, or they can attract each other.
Down, down, down.
If you have
Down.
unless you have control.
I'm realizing my policy of letting people just speak out and unmute might not work given how many people we have here. So unfortunately, I'll have to call on you when you raise your hand. I'm very sorry. I don't like doing that, but that's how we're gonna have to do it because I had no idea who was saying things just now. So maybe Aradi is how you say it. Give me your reasoning for what's gonna happen to the positive charges here.
I think it's gonna go down because we just said that conventional current goes from high voltage to low voltage, and conventional current is like the flow of, I guess, positive charge, which is really just like the absence of negative charge. So
Cool.
it's gonna go down.
Yeah, so you think positive charges are gonna go down. Anyone else have a different reasoning or a different answer? Arco?
Since in a circuit, for example, if you have a short circuit, which we're not going to use in the real life, so like the electrons, even though they actually go like negative to positive, the positive charge it like loops around and goes to the negative charge because it's attracted to it, kind of like a magnet, like where the opposites attract. So therefore, the high voltage, like the protons will go to the electrons, and yeah. Like
So I think
the positive goes to the negative and negative goes to positive.
you're thinking of it more
Yeah, like an
more
atom.
correctly than I intended. I'm pretending these balls here don't interact. And we're just thinking about where positive charges would go and where negative charges would go. And so what was said earlier about the positive charges going down and the negative charges going up was correct. So remember, current flows from high voltage to low voltage, right? That's where positive charges are going to flow. And we think about positive charges, we're thinking about conventional current. And if you think back to your Coulomb's law and electrostatics and things like that, electric field lines also go from high voltage to low voltage. It's not an arbitrary thing. That comes from how we define potential and define these things in physics. But the moral that I want you guys to remember is that current, when we do circuit analysis, it wants to go from high potential to low potential in the same way that I have a ball on a hill. It wants to roll from high gravity potential to low gravity potential. Okay. So yeah, Joel, question.
Also, the electric field lines in the high voltage to low voltage also indicate the direction of that positive charge would move, right?
Exactly. An electric field line is exactly the path that a positive charge would take in that environment. Any other questions so far? This is great, guys. Keep the questions coming. I appreciate that. Yeah, Ishan, is it Isha or Ishan?
Ishan. It just got cut off. I don't know why.
Okay.
Yeah. So like when there's a electric field line going from like the high voltage to low voltage, does it like, I mean, is it like a test charge that they talk about when it's like what direction that a test charge goes, and is the test charge always positive? Because I remember hearing that somewhere. So what is?
I won't say yes because I don't really know. I don't know what convention this book or whatever you read this from uses. I mean, generally, if someone's asking a test charge to tell you what the test charge is, like +1 coulomb, -1 coulomb.
Oh, okay.
But yeah, I guess you could assume it's positive and just state your assumption on the problem or something.
Okay.
But they should clarify. It's not immediately obvious, I think.
Okay. Yeah.
So I can see there's a lot of answers in chat already for this one. So we have a circuit with a resistor, and how much current flows through it. Everyone is saying 5 amps. And I think the reasoning is pretty clear without going into it. You have a 5-volt battery, it's resisted by 1 ohm. V equals IR, 5 over 1 equals 5 amps. So that's indeed correct. Now, how much power does the resistor dissipate? So how much power is the resistor getting rid of? Yeah, Omar?
25 watts.
Yeah, and how do you know that?
Since P is equal to voltage squared over R, square 5 is just 25 over 1.
Yeah. Or is there another way that you could think about this? So say you didn't have that equation. So yeah,
we could I squared times R since we find the current.
That's another one. But I was gonna say more So power, like definitionally, is current times voltage. That's the work that a voltage does. The fact that P equals V squared over R or I squared R, these are things that result from that. And so if I wanted to use the logic of P equals IV, how would I apply that? And maybe KVL might be helpful for this. Sorry, Ayush, yeah.
For me, I just well, first of all, obviously use Ohm's law to figure out that it's 5 amperes, and then after that, obviously you would just multiply the voltage and the current, and then you would get 25.
Yeah. So there you go. The key is that there's 5 volts across the resistor, and that 5 volts is pushing 1 amp of current. So power is defined by the voltage and how much work or how much current, sorry, I should say, how much current that voltage is trying to push. If I have 5 volts, but that 5 volts is pushing 0.1 amps of current, then that's only going to be 0.5 watts of power. But if I have 5 volts and that 5 volts is pushing 100 amps of current, that's going to be 500 watts of power. So
I have a question.
yeah,
For power, like I heard a lot of people say it's the process of converting from one state to another. So is it like converting the electrical current, in this case, a resistor, heat?
yeah. So
Or
the actual physics of like what a resistor is doing is not so simple, actually. It's not, there's no like clear thing you can point to that this is exactly what's happening in the resistor. There's some kind of complicated models that people have for modeling resistors. But very broadly, you can think of it like I'm pushing electron through material because electrons are what's flowing. And as those electrons flow through the material, they're bouncing off all the atoms within that material and they're losing kinetic energy. That energy is being dissipated as heat to the material, right? So you'll see this in a circuit. If you put way too much current through a circuit in a resistor that's not rated for that much power, the resistor will just light on fire because it's just too much heat for the resistor to handle. So that's a real risk. So you make sure when you use resistors, you see the power rating. That's the max power, as in the max heat that this resistor can dissipate. And so that's what I wanted to get at here. The current is what's pushing the electrons through, right? So if I have a ton of current, I'm pushing the electrons through really hard. And with a ton of voltage, there's a big force that's pushing those electrons through. And so those combine to lead to a lot of power dissipation. So remember, the big moral that I'm getting at here is that power is king. Okay, voltage is the force, current is what flows, but power is what actually results. Power is what we experience in the real world, like what the light is going on, what my computer is using, and so power is what matters. Joel, is there a question? No. Cool. Okay, so the other moral here is that the battery supplies 25 watts. And so in any circuit, the powers have to balance out. This is exactly the same as energy conservation. Hopefully, we are aware that power equals energy per unit time. And so when I say power has to be conserved, I'm saying the amount of energy that goes in every second has to equal the amount of energy that comes out every second. I can't put 10 watts in and get 12 watts out. That's violating thermodynamics. That's not a thing. However, I could have 10 volts into a circuit and then have 20 volts get dropped if I sum it up over all the components. KVL only applies for a single loop. So keep those distinct in your mind. Power will sum up to 0 over all the components. Voltage does not necessarily sum up to 0 over all the components. Only within a single loop it does. And so I answered that question right there. And so now this is the biggest moral of the day. Nodal analysis should be your de facto choice for circuit analysis all the time. I know there's a lot of push to use mesh, and mesh is fine if there's shortcuts that allow you to make your systems of equations easier with mesh. However, these simulation tools that we'll talk about, LT-SPICE, for example, they operate with nodal analysis. Nodal analysis is the minimal way of analyzing a circuit. And there's graph theory reasons you can think about for that, and very elegant mathematical reasons for why it is the minimal way to analyze a circuit. But nodal should be your go-to approach when you're presented with a circuit to look at. So, Joel, question?
No, I was gonna answer the question.
Oh, yeah, well, go ahead, answer it.
Some of the fundamental assumptions are charge conservation that holds true for Kirchhoff's current law. Obviously, I think conservation of energy.
So can you be more specific? You say charge conservation. Like, how does charge conservation apply to KCL?
So when you have a charge, say 1 amp, when you split it or when it say splits into two different paths, like a parallel circuit, the total charge will remain the same if you add up all the charges, negative and positive.
Yeah. So what you're really saying, I'll rephrase it, is all the current that goes in has to equal all the current that goes out.
Yeah.
Because current is just charge flowing per unit time. We just talked about power being energy per unit time. Current is charge per unit time. So you said the right thing.
Yeah.
But it's per unit time that we're really talking about for current. So
Uh,
let's do it.
I,
Oh, sorry. Yeah, go ahead. Omar.
I don't know if this is correct, but for some other assumptions, like we choose a node, for example, Vx, we always assume it's higher than the other voltage sources to like make the KVL equation,
So
or sorry,
you can
KCL
you
equation.
can assume it's higher, and usually if you're just making your math easy and not messing up signs, you do. But that is not actually like a fundamental assumption. That's just something you can do. Um, so and we'll do an example exactly like that, and we'll make that assumption. But you can get the same answer without making that assumption as well. Are there any questions in chat I should be looking at? Oh, so we're getting answers. Yeah, everyone's saying it. This one's easy. 1 amp, right? We have I can even draw. We have 5 amps going in. We lose 3 of those amps over there. We lose 1 amp over there. So there's only 1 amp left. And it goes out here. Now, the important point that I want to bring to your attention here, even though this is a very easy example, this is all one node, okay? Just because there's like 2 different junctions and a lot of wire does not mean it's a different node. When we talk about a node, we're talking about things that connect components. And so we'll see an example later today where this node looks really wacky, but it's still just one node. And so probably the most important part of nodal analysis is either redrawing your circuit to be pretty and not have to worry about these wacky nodes, or recognizing what the wacky nodes are and drawing boxes like these and just drawing arrows going into the box and out of the box like this and saying what goes into the box has to equal what comes out of the box. Okay. So that's the reason I draw a circuit so strangely like this. As another example, what are the question marks here? What do we got?
Can I say?
Yeah, go ahead.
Negative 3 amps.
Negative 3 amps. And that's correct. Negative is fine. Negative just means it's going in the other direction. So I have 5 coming in, I have 6 coming out, I have 2 coming out. So now I need 3 more to be able to accommodate that. So there's 3 amps going in this direction, or in the direction that arrow was drawn, negative 3 amps. Negative current is completely fine. That just means that it's going in the opposite direction of whatever arrow you assumed. And so that's going to be to what Omar had said earlier about assuming Vx is larger. If you don't do that, you might end up with a negative current, and that's fine. It just means the current's in the opposite direction that you would assume, and that's completely okay. So that's the moral there. Are we all good on the idea of what a node is in KCL? Any questions on that? It's really just what goes in equals what comes out. It's insane that Kirchhoff gets to be named for this thing. If I could be named for things this simple, I'd be a Nobel Prize winner. So, anyways. Okay, let's go on. So, get rid of the annotation. Sorry about that. So how do we use nodal in practice? Well, as was already kind of spoiled, we need to figure out the node voltages and then use Ohm's law to get currents. So let's actually solve out this circuit. What I want you to find yourself is how much power the 1 ohm resistor dissipates. So maybe I'll give you guys a couple minutes. Once you have an answer, don't send it in the everyone chat. You can DM me or one of the other instructors, and we'll let you know if it's correct or not. But yeah, take a couple minutes, try it yourself, and then we'll look at it together.
Wait, like what are we finding again?
In the yellow, how much power does the
okay.
1 ohm resistor get?
Okay.
What is Ohm's law?
What is Ohm's law? Ohm's law is the fundamental relationship for thinking about how voltage, current, and resistance relate. It actually, I mean, if we're getting like really pedantic about what it is, it's a kind of a deeper statement from conductivity and other like solid state physics. But for our purposes, Ohm's law is V equals IR. So I do think if that's a confusion that we have, if that's something that we haven't thought about yet, or something you haven't learned yet, you should go review the slides from last year and reach out to us if you need any help learning anything.
Is that an omega symbol?
Yeah, omega is an ohm. That's the symbol for resistance. So I'm not gonna lie. I did not write down the correct answer for the power. For this one, I wrote down voltage, and I'm realizing that now. So you can send us your answers for power, but maybe also send us your answer you got for the voltage across that 1 ohm resistor, because that's something I can actually tell you the answer for. I forgot to get the answer for the power. We'll find the power in LT Spice. I'll tell you what, we'll do that in LT Spice. So that's the beauty of circuit simulation tools. Okay, I have like 20 answers or so, so I'm gonna say that's enough for now. But if you haven't solved it yet, definitely go back and solve it again. This is a good simple circuit to get familiar with nodal with. So here, anyone watch 3 Blue 1 Brown? Anyone know that YouTube channel?
Yeah, it's very good for simulations and explanations.
Yeah, so
and also for like linear algebra.
I've been learning his animation package. And so this is something I made with his animation package, and you'll see it's pretty terrible. However, it gets the point across. So if you see strange things with this animation, keep in mind I have no idea what I'm doing. But it'll be cool. And over the course of these 9 classes, my animations will get better. So, okay, this is our circuit. Okay. We're gonna take the circuit. And first, whenever you do nodal, your first step is to identify the nodes, okay? So remember what we said, nodes are things that identify components. So ground is a node. And ground is the easiest node to assign a voltage to. Ground is 0 volts. We know that. That's easy peasy, right? Then from 0 volts, you can just trace your path up to get the voltage of other nodes. So from 0 volts, I follow this path. Through the battery, I'm going to gain 5 volts. And so when I get up here, I'm at 5 volts. Then same thing through this path right here. I'm at 0 volts. I go through the battery and I gain 2 volts. So when I get up here, I'm now at 2 volts. I want to do the same thing here, but I don't know how much voltage is dropped across this resistor. So I have to give it a variable, Vx, okay? So that's step 1 for nodal. Label all your node voltages, even if you're labeling with variables, okay? So we're going to label our voltages. Okay, so we're going to label our voltage, and then we're going to draw current arrows going into this middle node, Vx, okay? So pay attention, we're going to basically draw 3 arrows that go into that Vx node. So starting with this 5 ohm resistor, what is the voltage across this 5 ohm resistor corresponding to the current arrow shown? Can someone tell me?
5 volts.
It's not 5 volts.
5 minus Vx.
5 minus Vx.
Oh, yeah.
We're saying what's the voltage drop corresponding to the current shown. So it's going to be 5 minus Vx. And so when we put together the current equation for that arrow, it's going to be 5 minus Vx over its resistance, 5 ohms. So that's what we're going to put on that current arrow. We're going to do the same thing for this 1 ohm resistor. So for the direction of the arrow shown, what's the voltage drop?
Negative
Just Vx.
Vx. Negative Vx.
Okay, negative Vx.
Negative Vx, right? 0 minus Vx and then over 1. So that's what we're going to put on that current arrow. And then what about for this last one? What's
2 minus Vx.
Negative Vx
2 minus
over
Vx.
2.
2 minus Vx.
Exactly.
Yeah.
So now we have an equation. We have 3 current arrows going in and no current arrows going out. So I'm just going to say we have 3 things going in and nothing coming out, right? Because there's nothing else. And this is a perfectly legal way to state KCL because some of those currents can be negative, and negative currents, as we established, are completely fine. So then from here, it just becomes algebra. We all know how to do algebra. You get Vx is 1.18. Okay? So this is important point number 1. That's how you just do KCL, the very prototypical way of doing it. Okay? So any questions on that setup? I think it's fairly clear. Good. Definitely do a lot of practice if this stuff is going too fast for you. So yeah, so someone said, wouldn't it just explode from energy buildup? Remember that some of those currents can be negative. So like for example, we see Vx equals 1.18. So this green current right here, that's going to come out to be negative 1.18 amps, right? And so in reality, this current is flowing in this direction. So it's important to keep in mind currents can be negative. That just means it's going the opposite direction that we drew. Yeah, Benjamin?
What if we had all the currents going out?
Yeah, so you could do that too. And in fact, that's what the next thing is to show. So if I swap the direction some of the current shows, I only swap 2 of them, but you can swap all of them. You just, you just change your equation accordingly. So notice I2, it's kind of small. So that's my lack of 3 blue 1 brown skills showing. I2 became Vx minus 0. And then over here, I3 became Vx minus 2. But notice I1 stayed the same. And so now we have 1 current going in and 2 currents going out. And so our equation is going to say that. We have I1 on the left side here, and then I2 plus I3 on the right side. And if you solve this equation, you'll get the exact same answer. So with nodal, as long as you draw your current arrows and are consistent about what goes in equals what goes out, you'll get the right answer. It doesn't matter how you set things up. Yeah, Omar?
So when you said 5 over Vx divided by 5, if, for example, let's assume that the 2 voltage source is greater, would we say that like the greater voltage would equal all the currents exiting the Vx node? Or is it just based on the greater voltage source we make the KVL equation? Or
So I wouldn't read it as like the size of the voltage source. I mean, I could draw this arrow in this direction, could do that one in that direction, or I could do it in that. It doesn't matter what direction I choose. What matters is once I choose the direction of the arrow, I'm going to say it's this voltage minus this voltage, or this voltage minus this voltage, because we have voltage drop across resistors. Again, whether that leads to a negative voltage drop, meaning we chose the wrong direction and things are just going to be flipped at the end, that doesn't matter because the sign does not matter. It'll end up working out as long as we're consistent. Hopefully that was clear. So yeah, the last thing to show here is I can redraw the circuit however I want, okay? So once we set up our current arrows, this is the same circuit. I've just drawn the node in a weirder shape. This is also the same circuit. I've just drawn the node in a weird shape. And you can tell at this point I was just messing around with this animation package because this is not very useful to see. But the moral is currents going into a node. Again, here the node is just this whole thing. Currents going into a node equal currents coming out of a node. It doesn't matter what shape that node is. Node is just a segment of wire that connects things. Okay? So that's an important moral. Be clear on that?
Yep, good.
So for LT Spice, I'll show this really quickly and then we'll move on. Let me share my whole screen. Share screen. So you should download LT-Spice from this link. It works on Windows, Mac. I don't think it works on Chromebook, but Toby will show a different tool that works on Chromebook either today if there's time or tomorrow, or sorry, Wednesday. But LT-Spice will open. So this is what yours won't be dark mode. I had to make it dark mode because I'm a DGen. You'll put a resistor, you just press R to put a resistor. You press V to put a voltage source. And I'm just going to build up the same circuit. Press W to put a wire. And you'll learn the keyboard shortcuts as you use it more. But I'm just going to build it up quickly because we don't have much time. You always have to put the ground node. So again, you have to set where 0 volts is. Is there confusion? Then we have to we're going to set this one to 5 volts. This one's going to be 2 volts. 1 ohm. What was the circuit?
It was 5 on the left and 2 on the right.
Thank you. 5, 2. Then you can press this thing right here, run. Go to DC operating point and press OK. You can do the same thing by just pressing period on your keyboard and then typing .op. This does an operating point simulation. So it just simulates the circuit at whatever it's set to, the operating point, the Q point, or what you might call it as well. This is really useful for DC circuit analysis. When you get into AC and filters and stuff, you would do transient analysis or steady state analysis. Operating point is really for DC circuits. So I run this, and you'll see it gave me a bunch of these phi N003, phi N001, and notice this number 1.18 volts. That looks familiar, right? These are the node voltages. This is what LT-Spice solves for, first and foremost. This is why I emphasize node voltage as the method. It is literally what these simulation tools use. And then the currents are calculated off of that. If I want to see it on here, you can see if I go here, look at the bottom of my screen, it says DC operating point VN001. Okay. If I move my cursor down here, this is ground. If I move my cursor up here, 2 volts. From my cursor over here, 1.176. Now we cared about power, right? If I hover over the components themselves, you can see dissipation, 1.38 watts. Dissipation, 339 watts. Dissipation, 2.92 watts. So what would the dissipation be on this 5-volt battery? Can just someone guess? Is it like positive or negative? What's the dissipation on this battery?
Positive.
Positive.
The dissipation is negative 3.82
Oh, my bad.
watts.
Oh yeah, because it's supplying, my bad.
So why does it make sense that the dissipation is negative on a battery?
It is supplying power to the circuit.
Supplying power, giving power, not absorbing power like
Exactly.
the 2 volt source.
Exactly. It's dissipating. Oh, sorry. Okay. If we're dissipating negative power, we're supplying power. Does the power dissipated by a battery always have to be negative? In other words, does a battery always have to supply power?
No.
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 It can
Right?
absorb.
If I'm pushing current in like this direction and pushing a ton of current through it, then I'm gonna end up
It'll absorb
dissipating
power.
power to that battery because the current's going in the wrong direction. If you think about like your chemistry classes and then kind of how batteries work, we're basically pushing current in the wrong direction. And so we have to do work to make that happen. And so the battery is going to dissipate the power. It's not going to supply power anymore. And this is perfectly fine. This happens in the real world. It just means, generally it means you've done something wrong, but it can
I
happen
mean,
for any
for like
app.
rechargeable batteries, it would be like charging it, but like for non-rechargeable, that's really bad.
Yeah, that's a great way to think about it. I think that's true as well. It could be like recharging a battery, for example. I would think of that more like a capacitor than current going in the wrong way through a battery. But I think there's an analogy there. So I think that's a good point. So that's what I got for LT-Spice. We're kind of out of time actually. So Toby, I'm sorry, I'm gonna steal your show. But we'll start next time with how to use the non-LT-Spice tool for those of you who have Chromebooks. But if you don't have a Chromebook, please get LT-Spice. It's a lightweight software. It's super easy to use. It's going to be perfect for everything we do here. As far as
How do you get it?
you go to this link and you click download.
Can you put that in the chat?
I'll send out the slides, and you can get it.
Oh, okay. Thank you.
So we're running out of time. So do this circuit for fun.
Wait,
Don't do it.
where will you send? Oh, it's in there. Okay.
So there's your attendance code.
I have a question. Are we able to use the LT Spice program during challenges?
Yeah, challenges, of course. In this circuit lab, you can use Illustrator, you can use Claude, you can find your favorite professor from your local college and ask him for help. You can do whatever you want. I want you to learn, so there's no limit to your resources.
Where do
In
you
the
put the
actual-
attendance? Where do you put the attendance code?
Into the attendance form. I think it's this thing. I think
Oh yeah.
I will send the
Okay.
Oh, they actually made like a web thing.
But yeah, in the actual Science Olympiad event, I don't think you get LT Spice. Whatever.
Wait.
Also, are you gonna post some extra problems?
Oh, there's
on
the
Google Classroom?
Yeah. Toby got that.
What?
We'll make some problems at some point and send them out.
Oh yeah.
But worst case scenario, at least with this nodal stuff, there is stuff in last year's. We made some problem sets and I made comprehensive solution videos for them. So at the very least, for this first lesson, you have those.
Wait, what's the call?
It is First Circ Adv.
Very creative.
Oh.
First Circ Adv.
Arco, do you have a question? Oh, I cannot hear you.
Can you download LT Spice on like an iPad?
Can you download it? I don't know. I doubt it. If you have any sort of computer, maybe ask your parents for their laptop or something.
Okay.
An iPad might not. I don't know. Let's look it up.
Okay. Joel, do you have a question?
No, it's more of a comment. I know a good kind of also a good circuit runner kind of like LT Spice. I've used it on my phone and on a Chromebook. It's called Falstad.
Yeah, I think that's what
I don't think
Toby
it's as
suggested.
good as LT Spice, but it's pretty good, especially if you can't use LT Spice.
So
I don't think it calculates like the voltages and stuff. Just
No,
like
it does
mixing
calculate the
auto.
voltage. No, it does calculate the voltages.
Yeah.
List.
Yeah.
Is it a Spice tool?
Not too sure.
It is a splice. It is a splice tool. I'm running
Yeah,
it now.
I'm pretty sure this one's.
Okay, it's not a
Never
strictly
mind.
Spice tool. It uses a different algorithm.
Yeah.
But Spice is kind of the like
It
standard.
does work though.
way to do it.
Wait, for the attendance, it says that the attendance has already been taken.
That means you filled it all already. I think. I don't know how these things work. Was it Vihan? Did you say that? I'll make sure that your attendance is marked as you were here.
Yeah.
Bye.
I'll make sure it doesn't hallucinate.
If you guys want the other one that I'm going to talk about on Wednesday, you can download that. Attendance doesn't work. What? Thank you. Let Portugal.
I'm pretty sure everyone got an email for attendance or like the attendance link. So check your email.
Well, I'm telling you, the World Cup is scripted, bro. Simpsons already predicted it. Final match is Spain versus Mexico. I'm telling you.
Jaskra, what are you
And
yapping
Mexico's
on?
gonna win. Bro, Simpsons literally predicted it in the show.
Mexico's out,
buddy.
Mexico's out.
Mexico's out.
My God, you're autistic. Mexico's already out.
Yeah, bro, you never know, bro. The World Cup might give them a second chance.
Fortunately, that's gonna
Sure,
be
buddy.